Hello, everyone. For those of you who do not know me, I'm Paul Fischione, the CEO of Fischione Instruments. It's great to have all of you participate in our first virtual product launch. As you'll see from the upcoming presentation, Fischione Instruments has continued its tradition of innovation in ion milling. The company introduced its first ion mill in 1992 for TEM applications. About 10 years ago, we leveraged everything that we knew in terms of TEM and put it into our first ion milling system for SEM applications, and that was the Model 1060. About 3 years ago, we used the 1060 as the basis, again taking everything that we learned through its participation and incorporated those features into the Model 1061 SEM mill. The 1061 is achieving exceptional performance and is serving a very important market niche. Through our experiences with the 1061, we saw a significant market potential that was not being satisfied, and that is large flat-scale milling. For the past 2 years, our team has worked incredibly hard to deliver a solution, and I think that you're going to be very excited about what you're about to see. This is the Model 1062 TrionMill. It is a fully automated tabletop argon ion milling system that features highly flexible milling parameter adjustment. It offers large-scale milling in both planar and cross-section samples and creates the largest and most uniform flat area achievable by ion milling, with samples up to 50 millimeters that are effectively processed utilizing 3 ion sources. In addition to those characteristics, it provides the ultimate workflow for environmentally sensitive materials. The ion sources utilized in the TrionMill are 3 independently adjustable true focus ion sources, the same technology that we're utilizing in our other ion milling systems. The energy range is variable from 100 EV for gentle polishing up to 10 kV for rapid material removal. The beam current density is high, up to 10 milliamps per square centimeter, and the milling angle range is adjustable from 0 to 10 degrees, utilizing motorized ion source angular adjustment, with each of the 3 sources being at the same angle. Faraday cups are utilized for the direct measurement of beam current. This allows the ion source parameters to be optimized for specific applications. Additional key features is the ability of adjusting the spot size anywhere from about 300 microns up to 5 millimeters. High milling rates combined with low ion source maintenance make this an ideal instrument. This slide shows the relative position of the ion sources and ion beams. And this essentially is the secret sauce of the instrument. If you look at the beams in the upper position, you can see them aligned so that they cross at the center point, which is the axis of rotation. In the lower image, the beams are configured sort of in a bird foot type of configuration, and that allows the ions to project all the way out to the periphery of the sample. That's what produces the large milling area, and that's something that Pavel will be talking on in a little bit. The sample stage is capable of accepting both planar and cross-section samples. In the planar mode, the maximum size is 50 millimeters in diameter by 25 millimeters high, and in cross-section mode, it goes up to 10 millimeters by 10 millimeters by 4 millimeters. As with what we've done with many of our ion milling systems, the TrionMill features automatic sample height detection to establish the milling plane, and this adds to very repeatable results. Sample motion is either with full 360-degree rotation or rocking with variable speed, depending on the material characteristics and your desires for the specimen preparation. Instrument programming is through a touch screen. This is a 10-inch ergonomically adjustable screen where you're able to utilize and enter any of the operating parameters. Optional features. We've found that many samples are temperature sensitive. With this, there is an integral liquid nitrogen conductive cooling dewar with automatic temperature interlocks. You have the ability to program and maintain a specific temperature somewhere between atmosphere and cryogenic. We purposefully position the dewar access point to be close to the front of the instrument so it can be easily filled. There are interlocks in the system that if the stage temperature rises above a selected threshold, the process automatically terminates, which is very important if you're doing a run overnight when the laboratory is not being occupied. The cross-section station produces pristine cross-section samples by allowing the precise positioning of the area of interest in X, Y, and theta, or rotate. It's effective for a wide variety of materials. We have a lot of experience on semiconductor devices, multi-layers, ceramics, even polymers in terms of the soft materials, as well as hard, brittle materials. The prepared region is flat and it's free of damage for subsequent SEM imaging and analysis. The cross-section station accommodates a wide range of sample and mass sizes, and you're able to achieve multiple uses from a single mask. Another key characteristic of the TrionMill is the ability of transferring from a glove box or another vacuum chamber under vacuum in either inert gas or cryogenic. We've been doing this development in collaboration with Quorum Technologies in the UK. And if you see my cursor on the right, this is the interface on the front of the TrionMill. Behind there is the load lock gate valve, which separates the chamber. The sample is located. There's a door on the front of the transfer system which closes, allowing the sample to be contained in the vacuum or inert gas environment. A liquid nitrogen dewar flask maintains the temperature if you so desire during the transfer process, and there is a small ion getter pump that's battery operated that connects to the chamber that allows active vacuum pumping while the sample is being transferred from the TrionMill to the SEM or focused ion beam system. There's a magnetically coupled transfer rod which transfers the sample from the capsule into either the TrionMill or the SEM FIB. Additional options include in situ viewing with high magnification capabilities, and there's a choice of one of two microscopes, either 525x or 1960x. Located directly beneath the viewing window is a shutter that can be programmed. That prevents the buildup of sputtered material and preserves the ability to observe the sample in situ for prolonged periods of time. Image acquisition can be captured by a CMOS camera. The secondary monitor is particularly useful at being able to image the sample, and the image can be saved to a dedicated computer or transferred to another computer. Now, in terms of applications, I will turn this over to Dr. Pavel Nowakowski, our application scientist, who will go through the applications that we've done so far with the TrionMill.
Thank you, Paul. Welcome, everybody. I'm extremely happy to be with you today and having you with us. I will share with you some results obtained using our new model 1062 TrionMill, the most robust, versatile sample preparation system for SEM applications. So let's see what we can do using our model 1062. The first application I will start is semiconductor targeted delayering. As you can see here, it's sample after the process. We use for that purpose 3 beams crossing in the center of the stage. As you can see here, this is milled area. And why targeting delayering? Because we target one of the layer. In that example is a copper. As you can see here from MIDI-SD data, we go through this passivation layer, then first aluminum metal layer, and we stop exactly at the copper line. So now the question will be, how uniform is that delayering and how clean it is? So if you zoom into any of place of that area here, which is about 400 microns in diameter, you will see that it is extremely clean and you can easily distinguish the microstructure of copper. Another question is, how uniform is that delayering? So we did a cross-section, fib cross-section in the center, one in the extreme of the milling area. As you can see here, the cross-section, one in the center and another one 150 microns from the center. So you can see the cross-section are very uniform, very similar. And if you look closer, you will find the uniformity of the milling is 50 nanometers over 300 microns. So it's very nice and clean, the target delayering process. So now we'll go to the large area milling. But before, a few words why we will show a lot of EBSD results. So we use EBSD technique to assess sample preparation quality. So as you know, the EBSD technique is very sensitive for any sample preparation artifacts, like scratches, as you can see here, induced deformation on induced phase change. So we use EBSD technique to see how good our sample preparation is. As you can see here on that example, the initial phase of ion milling, we still see some scratches from mechanical polishing and induced deformation. While we mill, we remove the scratches, we remove the deformation, and post-milling image show a native structure of the analyzed material. So that is the reason that we will show a lot of EBSD data. So then I will move to the cross-section preparation. It's very demanding application. For instance, for failure analysis. And here we have the solder bomb cross-section. This sample was not at all mechanical polish, just the mask was posed aligned at the center of the solder bombs. All material above the mask was removed by one cut using TrionMill. As you can see here on that image, we have perfect cross section about 5 millimeters width of 12 solder bombs, and you can zoom at any area on that cross section and do failure analysis. So you can see here, you can clearly distinguish the microstructure of solder, and the interface is very clean between the solder and the copper pad. You can, of course, do any analytical measurement that you wish for your failure analysis, identify all the phases present in your solder bombs, and of course you can do EBSD that will show very excellent quality data, EBSD obtained from any of the 12 solder bombs present here. As you can see, you can study the phase distribution on crystallographic relationship between them. So the next example is austenitic steel. You can see here the sample that is 18 by 18 millimeters. So we milled it by TrionMill and collected the images from whole area, then stitched them together. So as you can see here, if you zoom at any place of that sample, that big sample, you will see that the structure is very uniform. You can see very easily the austenitic steel structure, distinguish all the grains and see that the milling was uniform across all the samples from the center to any corner or edge of that sample. Another example is very interesting, multi-phases mineralogical sample, which has some porosity, which makes it very difficult to preparing for any sample preparation technique. This sample has dimension of 25 by 20 millimeters, and it made basically from corundum grains, which are these big grains here, surrounded by anorthite, mostly by anorthite. As you can see, we obtained a very high, a good quality EBSD pattern across whole surface of the sample, which is quite big. So it is showing the EBSD pattern here, or band contrast mapping overlight of the sample. This sample is very challenging for analysis for that reason that the grains are very change the size from millimetric size for corundum up to tens of microns from for anorthite and orthoclase. Another example is martensitic steel. Here you see the sample dimension 28 by 10 millimeters of martensite. As you can see here, the image forward scatter electron contrast, which showing very sharp crystallographic contrast. As you can see here, the lots of martensite, and that also showed that the topography, surface topography after all ion milling is very shallow, because this is very important if you want to get such beautiful images like this one. Another slide is showing the corresponding EBSD map was acquired at quite high speed and quite high binning. As you can see here, we got very nice and high quality EBSD data obtained from whole big area, almost 30 millimeters width sample. And if this is still not enough for you and you want to or you need to polish bigger samples, bigger area, you can easily polish the samples up to 550 millimeters diameter in area. As you can see here, we have an example of the copper bar, 48 millimeters by 12 millimeters. As you can see here, there's log of model 1062 with the sample sitting on the stop after milling process. So once again, we collected a lot of images, SEM images, EBS data for whole area of that sample. So you can see here, there is example of images collected in the center at the edge. If you zoom to the images, you will see as it's extremely clean and uniform milling over a whole area, and you can easily distinguish the microstructure of the copper. If you go to the one of the corner or edge of the sample, you will see the same high quality milling which show you microstructure of the copper. So we collected, of course, EBSD data to show you that the surface quality is very good. This map showing the center of the milling, and another IPF map showing the right bottom corner, which is 24 millimeters from the center. As you can see, there is the EBSD data are the same quality as for the center, as for the periphery of the sample. So the question now is what you can get from so huge amount of data that will be collected from the huge sample like that 50 millimeters width. So you can improve your statistical measurements like grain size or texture. And here is example of average grain size that we calculated for our copper bar, which is 250 microns. It was calculated from 6,000 grains. As you can see here, this is only calculated from small fraction of the sample. So you can imagine how good statistic you will get being able to mill big sample, such big like 50 millimeters in diameter. Another slide is showing set of pole figure that was plotted from 5 million data points, showing very strong texture along 111 direction for our copper bar. With that conclusion, I will turn over to Paul. Thank you very much.
If you'd like additional information, feel free to contact us. We can set up a phone call. We can set up a webinar. We can work on your particular materials. This is an exciting new development for us. I really appreciate everybody's interest here today, and hopefully look forward to working with at least some of you to get this system into your laboratory.